performance comparison between two congestion control algorithms in VANET channel. And this is a joint work with Ali, Marco, and also the researchers from Toyota Info Technology Center, USA, and also the Volvo Technology at Sweden. I think we have mentioned the VANET concept this morning. So this has been being believed that wireless vehicle-to-vehicle communication holds a great promise for significantly improved traffic efficiency. So let's assume if each car has the ability to talk to each other and form a vehicular ad hoc network, so we can provide several services like collision avoidance, road hazard avoidance, and road guidance. Those things has been imagined for a long time, but recently IEEE has 11P standard and specifies the MAC and the physical layer protocol. So based on the 11P, DRCRC technology has facilitated the deployment of the VANET. So recently, the US government has announced attention to require DRCRC devices in the new car within a few years. And also in the Europe, 12 members of car-to-car communication consortium pledged to begin equipment of DRCRC at their new cars by 2015. So it seems everything it seems the imagination gonna realized, but as mentioned in this morning, for those kind of vehicle-to-vehicle communication, we have several common features. One is those kind of safety message is periodically broadcasted. So this message gonna including some information like location, speed, heading. Those are all timing messages. And since those kind of messages is periodically broadcasted, so when the node density goes to very high, the channel load is gonna be very high. Actually, DRCRC use a CSMA CA mechanism, so it can be mitigate the collision at some extent, but we observe that the frame collisions still occur. So there are some field tests shows that around almost 80% packet loss for the links with RSS at the level -80 to -85 dBm with almost 400 vehicles density. So we can conclude that the high load on the DRCRC will lead to reduce the successful communication rate, so that we will compromise the mission of the increased road safety, since those kind of safety messages cannot be successfully delivered. Okay, one more thing I want to mention here is we talk about a lot about those safety messages. So actually, those kind of safety messages has been defined in the standards. In US, the safety message is called a basic safety message, and in Europe, it's called CAM, corrective awareness message. So those kind of message while providing the information about position, timestamp, hiding, speed, driver direction, past history, and vehicle type. In US, BSM, the generation rule for BSM has not been specified. So right now, in most trial and field tests, they use 10 BSMs per second as the rate. And for CAM, they have a very complicated generation rule. There are two conditions for generate one CAM. First is the time condition. So basically, the message interval should be larger than a certain threshold. This threshold is defined by the DCC. We will talk about DCC later. And another condition is called the dynamic condition. So the dynamic condition is about heading speed and the distance traveled. Besides the two conditions, if there is a message generated in the last 1 second, and then a new cam will be generated. So the largest message interval will be 1 second. We have talked about the channel load. High channel load has a better effect. Okay.
So you are talking about speed or the velocity there?
Yes.
You are talking about the speed change 0.5, so it's not velocity, it's speed, only the magnitude, right?
Yes, the magnitude. Yes. So we have talked about the high load in the channel. So here is some kind of solution to control the channel load. The variable we can control here is a message rate. So the idea of the message rate control is kind of simple. So each vehicles compute a rate which they can use to send a message, and this rate should be calculated based on the channel load. Practically, the channel load is measured. Is indicated by use the channel busy ratio. That is the time ratio of the time ratio of the channel in the busy state. So the goal for this message rate control is we have a controlled load. So the load should be not too high and too low, and for each rate we should have a converged rate. For each vehicle we should have a converged rate, and fairness, that means each vehicle has equal opportunity to contribute to the congestion or equal opportunity to transmit. We're gonna discuss two directions of the message control algorithms. One is adaptive control. The representative of this kind of control algorithm is called LIMERIC, which is proposed by the Toyota. So the idea of this algorithm is kind of simple. So we provide this threshold, or we call it target CPR. Here, this CPRG is a target. So given alpha and beta, the next rate is calculated based on the error of the current channel busy ratio and the target channel busy ratio. So what is alpha and beta? Basically, those kind of parameters control the converged speed and the stability reboundness. And another control algorithm we discussed in our work is defined by the European Telecommunication Standard Institute. So this kind of control algorithm is simple. Basically, according to each channel load, we define a rate and use this rate to generate a packet. So that's this is simple idea. The channel rate basically the control process is basically a table lookup process. And for this kind of algorithm, we don't reach control load because we don't have that target CVP, and we don't require the convergence and also the fairness. Everybody just look up the table based on the current channel load, decide a rate. For the comparison, besides the LIMERIC and the CAM DCC is we use a generation rule for the CAM message, and also use the DCC we just mentioned before, that lookup table to control the rate. Besides we compare those two algorithms, we also provide other two generation rule as a reference. One is 10 Hertz. That means no matter what the channel load is, it just periodically generate a packet at 10 times per second rate. And for 10 hertz DCC is we generate the packet at 10 hertz, but we use DCC to sharpen the traffic, traffic before it goes to the MAC layer. So this is topology we use to simulate. It's a 4 kilometers highway, and in the middle we have a winding part. Why we have this winding part? We use this winding part can create a high dynamic. So we wanted to study the algorithm performance under a high dynamic scenario. So this simulation is used as to simulator, and the number of vehicles we discussed in this work is 500, 1,000, and 1,500. And the power here we use 10 dBm. Actually, the equivalent to the transmission range equals to 500 meters. And the CPR we mentioned before used to indicate the channel load. We measured them. We measure the CPR every 100 milliseconds, and most importantly here I need to mention is every node measure the CPR at the same time. So and the other parameters used in LIMERIC is the target CPR we use here is 79, and the alpha is 0.1, and beta is 0.033. So here is some result. First we're going to show is the channel BZ ratio. We can see here the black dot indicates the channel BZ ratio of the CAM DCC. So the first impression we can have is there are huge oscillations in the CAM DCC. And compared to the CAM DCC, we can see the green dot indicates the LIMERIC. They can converge to a certain channel load. So it basically can tell us the LIMERIC control the channel load at the basically very close to the target channel load. But the CAM DCC suffers from the variation. We also calculate the mean CPR here. For the LIMERIC is around 68. For the CAM DCC is 50. But from here, this slide shows packed error rate, packed error ratio for the four algorithms. We can see here, although here the CAM DCC has a lower channel load, but it shows a very high packet error rate. It's because the oscillation we have observed. But compared to that, LIMERIC reached to comparatively lower PR. Another metrics we use to evaluate the performance is interpacked gap. The concept of the interpacked gap is time between two consecutively received packet from one sender. So this matrix can measure can measure how fresh the message can be received. Here we can see the similar phenomena. The right curve indicates the CAM DCC is reached to very high. It's because it suffers from the oscillation lead to a very high packet error rate. And the black curve indicates the LIMERIC. Basically, it's outperformance other algorithms. And another thing I wanted to mention here is this curve. This blue curve indicates the 10 hertz. It's actually in the very short range. It outperforms other algorithms. It's the best. And until 125, it goes to worse, because at the short range, the 10 hertz it has a comparatively low PR, so they can have fresh information. Yes.
Could you just elaborate on the x-axis? I mean,
it's let's go. So all the result we show here is all calculated in that range. That's winding range. And so what we calculate here is distance being the result. So for how it calculated for a receiver, I calculate the packet error rate for the senders 25 meters away from me, 75 meters away from me, 125 meters away from me, and that's for one receiver. We calculate all the receiver in that winding part. If they are in the winding part, we collect those metrics and get the average. That is how the result calculated.
But that implies that, I mean, you have some of them go in between, or this is your resolution, of the distance. I mean, there may be some receiver that is 50 meters away, or 100 meters away. They're not shown. Is that right?
Oh yeah. So.
Okay. Fine.
Okay, so we have the similar conclusion here. Here we have the, this is for the 1500 nodes result. We have here the LIMERIC outperformance other algorithms, and the CAM-DC, since it suffers from oscillation, it shows much not much worse result. And we can study why the CAM-DCC has those oscillation. So first thing, we plot the number of transmissions in a random choose 1 second. So what we show here is the number of transmissions in 1 second for different algorithms, and each bar here indicates the number of transmissions happen in 100 milliseconds. So what do we see here? The LIMERIC, the number of transmissions of LIMERIC can be like uniform distributed, but for the CAM-DCC, you can see there are some kind of blink region here. That means there are no CAM generated and transmitted in that time interval, and all the transmission. It seems the transmission here is clustered. And another thing we studied is we mentioned that before. All the CPR, the CPR for all the node is measured at the same time. We think about is this contributed to the synchronization in the CAM-DCC? So what we did is we desynchronized those CVP measurement. But what we have is the left side is CPR result for the unsynchronized CPR measurement. For the right side is synchronized CPR measurement. What we have is unsynchronized CPR measurement can reduce the synchronized oscillation only to a little bit amount. So there must be some factors contribute to the oscillation in the CAM-DCC. This is also the topic we are working on right now. So let's conclude the presentation. We have compared two algorithms, congestion control algorithm. One is adaptive control algorithms. They can have a target CVP, and they trying to tuning the rate and make the channel load towards that target channel load. And for the reactive control algorithm, they don't have those kind of control the load and the convergence and the fairness property. And they also suffers from the oscillation. Okay, thank you. Yes?